Hi everyone, are you able to see the screen?
Yes,
Hello?
sir.
Yeah, okay. So, what has been done in the class now? The vector space, subspace, and bases. Okay, these all things I think the group. Okay, so I just list what we are going to do for the tutorial one. First is the vector space, next subspace, bases. Harshita, are you asking something? No, your hand is raised. Okay. Bases and I think the groups. What is a group basically? Okay, so first we define what is a vector space. Do everyone knows what is a vector space? I think so. Okay, so I'm discussing the assignment questions, but I may not be providing the solutions of them. So you just work on them. But I will provide like how to approach those questions and we can discuss that. Yeah. So hopefully you are knowing the vector space, but I just recall the definition of what is a vector space. Students are coming as okay. Yeah, so let's define what is a vector space. So for that, I need to first define what is a field. Do you know what is a field? And for that, I need to first define what is a group. So vector space can't come usually like it. Wait a second, why these everyone is coming? So the vector space is definition is dependent on the field and the field is dependent on the group definition. So first of all, I need to define what is a group. Then I go to field, then I go to vector space. So what is a group? So I just define that. And for the group, I need to define the binary operation. Okay. So what is a group? Let's define that. Okay. Yes. So a group is basically, so first define what is a binary operation between, yeah. Okay. So if you have a set A, that means, right? Suppose, so I'm defining what is a binary operation. Suppose we have a set A. Suppose there is set A. Then you define a function star, which goes from A cross A to A. Okay. So a star takes element from A Cartesian product with A to A. So what is a Cartesian product? Do you know what is a Cartesian product? So A cross A is the set of elements A, B such that A is in A and B is in B. Okay. This is the Cartesian product. And you take out the elements from A cross A and then just transfer it to this A set. And how do you transfer it? Suppose A is set of real numbers, right? Then you just transfer, like you just take A comma B from R cross R. And what does star is doing? Star is transferring the elements from R cross R to R. How it is transferring? So that you have element from R cross R and it lands into R. So how does it happen? So we can take A, B and shift and transfer it to say A plus B, right? So which is in R, like this. So this is one sort of binary operation. And similarly, you can define other binary operations. And so the main property of the binary operation is, okay, so binary operation is just a mapping basically from elements of this set R cross R to R, or any set A cross A to A. These are all coming late. So it's just a function. It's just a function from a set, this one, A Cartesian product of A Cartesian product with A to A. Here A is R, so I've just taken for an example. So it just sends a tuple from R cross R to R. So it's just a function. So using that, we define what is a group. So I just write what is a group. Okay. So so if you have a set A again, and then you say if you have two elements, you define a binary operation. Binary operation. Let me see, the volume is down, I think. Yes. Define a binary operation, say star from A cross A to A. Okay. And you say that if, so how does this binary operation works? So if you have star which sends elements of A cross A to A, then first property it should satisfy is the closure property. So closure is just you take A star B where A B is in A and B is in B, such that this A star B belongs to A. Okay. So that is the closure property. You take two elements from the set A and their binary operation gives you the element in the set A. That is the closure property. Second property is the, that's by definition of binary operation as well. So it's not a problem by definition. Binary operation. Okay. Second property is identity. Okay, no, associativity. So just, so how does it work? So you take any three elements, A, B, C, which belongs to A. Then you just consider A star, B star, C. It should be same as A star, B star, C. Okay. That is associativity. Third property is your identity. Identity. So what's that is, so if A is any element from A, then you just have something like A star E is A, then E, or E star A is A. Then E is identity. E is identity. Okay. And fourth one is the inverse. Inverse. So what is an inverse? If you have something like A, okay, B is called, let me write. B in A is called inverse of inverse of A in A, such and if so B is called inverse of A in A if B star A is identity or A star B is identity. Okay, so I just write and so that is called as inverse. So these four conditions are required for a set to be a group. Do you understand this? I hope you know before, but I just recalling these things. The next thing is field. What is a field? So field is just a group with some extra property which is called as so field F, let's say denote by F, is an abelian group. Abelian group. Okay, field is an abelian group. And there are two operations in the field. Okay, so F, yeah, so field is like a group with two operations which has plus and dot. Let me write. Where F with D, this is the star one operation, this is the star two operation. So F in the star one operation, which is called addition operation, it forms a is an abelian group. So I just write F is an abelian group under addition. And F with is star 2. So it's like F just because in addition, in additive group, you say that identity is just 0. So you just remove identity and then you take the operation star 2, then it forms an. This is the first thing. This is the second thing. Is an is a multiplicative group. So another operation is the multiplication group. So that is the case. Okay. So it's just a group. Um, Wait, is an abelian. Let me write it more clearly. Is an abelian group under multiplication. Okay, now we can define what is a vector space. So a field is just a with two set of operations. If you have a set and you just give one operation which is the addition and another operation which is say different multiplication. For example, what are the examples? Can you give me examples of a field? Examples. What are examples? R forms a field with positive and dot with multiplication and addition. Is that form a field? Is a field? Is it? Can anybody tell me, is that a field? Anyone? Anyone wants to answer it? No. Okay, whatever. So Z is not a field because I just write this. Z is not a field. Why it's not a field? Anyone? Because if you have element from Z minus 0, then can you find such elements such that A star B is 1, which is multiplicative identity? Can you find that? No, right? Because this is just multiplication. So A into B is 1, means that B is 1 upon A, which is not possible because A is in Z, but B is not in Z, right? B is not in Z. So what happens is that Z is not a field in that case then, okay? Because every element has no inverse except identity. All right, so this is one example. And another thing I want to make sure is, okay, so we define what is a subspace. Okay. Oh, sorry, no, subspace. I define what is a vector space. Okay. Okay, so what is a vector space? So this is a so let denote it by V. So we say that V plus is an abelian group. Oh, I haven't defined this before, I think. Let me see. So what is an abelian group? Yeah. So abelian group is A star B same as B star A. Okay. That is a commutative relation like associative, but it's different relation. That is one another property. I haven't defined, you should have told me. So A star B is B star A, that is one other property. If a group follows that property, then it say that the group is an abelian group. All right. So V plus is an abelian group. Okay. That is the one property of a vector space, that it needs to be an abelian group. Then you have a field. Suddenly the field comes here into picture and it satisfies some operations with your vector space V. Okay. So there is a star, say star is an operation from, now it changes from F cross V to V. Okay. How does it work? What are the relations star satisfies? And there is a relation from V cross V to V as well. Think so. Yeah. So what are the operations star satisfies? So first operation is that if you have A star B star V, then it should land up with A. So um yeah, this is one confusing relation. I think I should use another notation for that. Or should I use? So A is a member in the field. So this is the first property. A is in the member in the field, B is the member in the field, and B is the member in the V. Okay. Then you say A is in F, B is in V, and B is in F and B is in V. Then you get AB, which should be in F, and then you have V. V. Yeah. So whatever I'm denoting is that there is an operation going on inside the field F. There is separate operation star, which from F cross V to V. So I have to separate both the operations. So, and yeah, so A star B star V is AB star V, where this, if I am not using the star, then it's an operation under F, right? So this is the first property that you usually expect, that you should expect. And another property is that if you take 1, 1 is a multiplicative identity in the field F, and you just multiply with the star V, then you just end up in V. Okay. Third property is your A star U plus. So U and V are elements in the V, so I can use the plus operation because V is an abelian group. Uh, V plus, I'm using the plus notation under addition. Yeah. Then you get A star U plus A star V. Okay, which is an element in V. Fourth operation is your A plus B star V, same as A star V plus B star V. So all land up in V. Here star is from F cross V to V, and it's also a binary operation, but not from V cross V to V, but F cross V to V. Till now, anyone has any problem in understanding, then they can ask so that I can move to question. So what is the example of a vector space? Yes, so we just write V and F. So you just, because this F came suddenly, so I just put in the bracket. So VF. VF is a vector space over field F. Let me know if you have any questions. So R over R is a vector space because it satisfies all the properties. R is an addition. R is a abelian group under addition. R is a field, right? So it is a vector space. All right. Any other example you want to give? Set of complex numbers over R, right? Uh, Matrices, set of matrices over R. These are all the these are all the vector spaces. I'm not going to more complicated ones, but these are that. Yes. Okay. So what is a subspace then? What is a subspace? So I just write the definition of a subspace. So a vector space W is subspace of vector space V if A, B belongs to W, then first property, what does it satisfy? A plus B should be in W. Second thing, it should be if I'm taking alpha from a field F, then alpha A should be in W. Okay? So ultimately what happens is that alpha A plus B should be in W. That is a combined property for a vector space W. All right? So these are the some things that I want to recall, and if you have any queries, just ask me. Take a couple of minutes understanding that I give you 10 minutes to understand all these, and then we have questions, then we will discuss that because it's the first class, so I want to discuss this. So basis we will discuss soon later, but first we will need to understand these things. Just see them. Okay, maybe I can minimize it. Don't know how to separate it. How does it work? Okay. Is these things clear to you? Or I just write a question and you try to solve it first? Okay. I just write a question and then we just try to solve that. Okay. It's related to your assignment, and I think it's, yeah, I just discussing the assignment questions, but I will discuss, I will not be providing the solutions, but we'll discuss from you. So what is the first assignment question of your? Consider the vector space V equals to R3R. Which of the following are subspaces of V? A. W1 is this X to Y 3Z such that XYZ is in R. W2 is XYZ such that XYZ is in Q. C. Both A and B. D. None of these. None of. I won't tell you the answer, but we will discuss the step-by-step procedure. Okay. So, do you take some time to solve this? Okay, just solve it for 5 to 10 minutes. I will be back. Okay, so has anyone done this? Yes or no? So
Yes,
W1, yeah, okay, not asking for the answer, but how you follow the same procedure that I've discussed? You understand everything? Okay. So according to you, what should be the answers, by the way?
A.
You don't know. A should be answer. Okay, whatever. We are not saying about the answers, but just discuss the solutions and we trying to see if we can apply the same logic. So we have subspaces. Which of the following are subspaces? So in this question, you need to understand, you need to have the definition of a subspace in the mind while discussing this. So if you say about W1, then is W a subspace of V? So V is R3R. So it should satisfy all the properties. Like if A is in W1, B is in W1, then A plus B should be in W1. Okay. So this is the first property of a subspace. So if you can see, the elements in W1 are like X2, Y3, Z, and they are all elements from R. So if you just sum them, then they are elements of R, of course. Okay. And the another thing is that alpha A should be in W2, W1. So alpha is any member of R. Also, it is very clear that if you multiply any element of W1 by a real number, then it also is in W1. So W1, I think so it qualifies because it satisfies all the properties. Next about W2. Yes, what is the problem with W2? Does it satisfy this? All the properties of a subspace? So if you just sum them, if you take any two elements from W2, X, Y, Z, then the same properties I'm asking. So sum of two elements from W2 is in W2, right? That's clear. But next thing is about if you multiply any element of W2 by a real number, then does it land in W2? That is the question. So this is the question I need to answer, get an answer from your side, and you can still answer it. So it may or may not be. So you just check the second property. If it works, then it's good. If it doesn't work, then it's yeah, it's no, it may not be correct option. If it works, then it is a correct option. So the problem is with the second property. Just check the second property. So whatever the answer will be, but you are able to use whatever I've discussed. Yes. So this question is very much clear, I think. So I can move to the second question. And the second question is that suppose the vector v is 5, 18, 22 is in R3, is expressed as linear combination of vectors v1 equal 1, 2, 3, v2 is equal to 9, 1, 2, and v3 is equal to 4, 5, 6, such that x is v is x v1 plus y v2 plus z v3. Then what is the value of x? Then what is x? Just find the value, just try to solve it and try to find out the value of x. Yes, and x, y, z is in R. So I'm not interested in finding the value of x, but I'm interested in, from this question, I'm interested in how to write v as the linear. So suppose you have a vector space R3, how do you write a vector from that space as a linear combination of three other vectors? So I will discuss it. Just take some time. Like, how do I write? How do you write the vector as a linear combination of other vectors? Just try to take some time and work on it. Okay, 5 to 10 minutes again. Yes, so and have you tried that? Okay, so I just try to write that. So you have to express V as the linear combination of V1, V2, and V3, right? So what is V? So I just try to write in this way: 5, 18, 22. And it is X, Y, Z. So it is sometimes like X, V1. What is V1? 1, 2, 3 plus Y. What is V2? 9, 1, 2. What is V3? 4, 5, 6. Okay. So just separate it into entry wise. Then you just have X5 is X plus 9Y plus 4Z. Then 18 is 2X plus Y plus 5Z. And 22 is 3X plus 2Y plus 6Z. So you can solve this system of equations. So first, second. So just solve 1, 2, and 3 simultaneously to get X, Y, Z. That simple it is, right? So if you want to express a vector as a linear combination of other vectors, then it just reduces to a system of equations and you know how to solve it, right? Am I right? Okay. So I just go with another question. Okay, so I'm discussing the base subspace first, then we discuss the basis. Okay, so if W1 is your this, it's 5, such, sorry, such that and W2 is this, such that so these are subspaces. So W1 and W2 are subspaces of R5. Then what is the dimension of? Okay, so I think I have to discuss the basis first, then we just discuss that. Okay. Okay, so W1 and W2 are subspaces of R5. Then you need to find, for the time being, you need to find is W1 intersection W2 a subspace, W1 union W2 is a subspace. Just check these things. Just check these things for 5 minutes and then tell me. So, okay, just check. In meantime, you also check this thing. You just write which subspaces of, so P is the set of all vector space of all polynomials over R. So okay, just write it. You know all polynomials, right? How does it look like? Polynomials over R. Then I'm writing about these sets. The set P in P such that degree of P is equals to 4. So this is one set. Second set is P in P such that degree of P is less than equal to 4. Third, P in P such that degree of P is greater than equal to 4. Then check are these subspaces of P? Capital P? These are small ones. So just check these two questions and let me know the answers. Just take it some time and 5 to 10 minutes and yeah, let me know the answers. How do you approach it mainly? Okay. Yes, tell me. What approaches you use, sorry, for the first one? So W1 and W2 are the subspaces of R5. That is very clear, if you can see. And the other thing is that W1 intersection W2 is a subspace. So so that is also very clear. If X is in W1 intersection W2, Y is in W1 intersection W2, then this X is a part of W1 as well and W2 as well. Similarly, Y is a part of W1 as well and W2 as well. Since W and W2 are subspaces, so X plus Y should be in W1 and X plus Y should be in W2. It means that X plus Y is in W1 intersection W2. And similarly, you can check the other property. So W1 intersection W2 is always a subspace, whatever the W1 and W2 are. So it's always yes. And W1 union W2 is a subspace or not. So in this case, we just confine to that. So W1 union W2, what elements look like in W1 union W2? Either this type of elements or this type of elements or the sum of both. So is it a subspace? What is W1 union W2 here? What is W1 union W2 here? Anyone? Anyone can answer. So W1 union W2 is all space R, I think. R5. So it's just R5 over R, and that is a subspace. But you can see that W1 union W2 is may not always be subspace. So mind that. Sorry. I just use not that W1 union W2, sorry, may not be a subspace. So when it's a subspace, it's a subspace when so W is one is contained in W2 or W2 is contained in W1. Then it's a subspace. Okay. Yes. So in this case, it is a subspace, but it may not always be the case and depends on the condition of one is containing another one, right? Let me charge it. Yeah, so what about the next question? P is the vector space of all polynomials over R. Are these subspaces of P? P in P such that degree of P is 4, degree of P is less than equal to 4, degree of P is greater than equal to 4. So let's discuss orally about the first one. Degree of P is 4. So if you have two polynomials and suppose the degree of polynomial is 4, what does a 4-degree polynomial look like? Okay. Why is I'm echoing? 4-degree polynomial. Tell me. It's like a4 x4 x cube plus a2 x square plus a1x plus a naught. So this is a typical 4-degree polynomial. Why am I echoing? Oh, I think problem from your side. Yeah, so this is a typical 4-degree polynomial, and you have to tell me like If you sum these types of polynomials together, then it will again be a 4-degree polynomial, right? That is very clear. Another thing is that if you multiply this polynomial with, say, alpha, where alpha is in R, then you get a same a same polynomial of degree 4 by multiplying. So that is a subspace for sure, I think. And degree of polynomial is less than equal to 4. Degree of polynomial is greater than equal to 4. So second is the degree of polynomial is less than equal to 4. And okay, that's a second, I think. So if you just sum two polynomials of degree 4, will it always give a polynomial of degree 4? Suppose I am taking this polynomial x4 plus x cube plus x square plus 1. And I'm taking another polynomial. Then if you sum them, then it's just x cube. So this thing has gone, right? So it's not a, so it is not satisfying the first property. So how do you say that this first one is a subspace? So first one may not be a subspace because it is not satisfying the first property. If you go to the second one, degree of polynomial is less than equal to 4, then in that case, what you will say? What is this a subspace? So if you have sum is always less than equal to 4, and yes, I think it is a subspace. And degree of polynomial is greater than equal to 4. In that case, it may not be a subspace, right? Because if you have two polynomials of degree greater than equal to 4, then if you have summed them together, like the previous example, then you may end up in getting a polynomial of degree less than equal to 4, which is not a subspace. So the answer is in your hand. Hope you understand it. Let me go to other questions. I will write two more questions and then ask about the groups. Okay. Okay, so the another question in the box is this. Question 5 is, let G star be a group where G is this X, Y, zero and AB, CD is AC plus BC plus D for all AB. Then the identity of element of G star is then. So you have to tell me what is the identity of G. Just perform the similar operations like what you have done. So um, this is obviously a group. You can check it. Then find out the identity element of G. Okay, just try to work on it. Then I write another question. Yes, have you tried it? Okay, so to find the identity of G, let's try to solve it. So you need an element A, B such that you get E1, E2, and you get again A, B. Okay, this is the identity, what you call as identity, right? So A star E, this operation is defined using this one. So AC, BC plus D. So A E1, B E2 plus, oh, sorry, this is E1 plus E2. So it is just AB. So from that, from the first equation, you get A E1 A and B E1 plus E2 is B. So you can solve it to find out what are the values. So I just solve E1 is 1 and E2 is 0. So 1 comma 0 is the identity. Okay. So identity of G is 1 comma 0 tuple. So that is originally coming from the group definition. That is very easy. Okay. Now I write another question. 6. Let star denote on set G, which is given by 1 plus 2m and is in Z, then which is true. Star is then which is true means you have a star is associative, commutative, binary, okay. Just try to find out that what does it star is. Associative, first you check binary, then associative, then commutative. Let me know this. Then we will discuss about something about the basis and spanning set, and then yeah, some couple of questions on that. Just try this. All right. So have you tried it? So we just try to find out what is. So is it binary really? No, no. A big no, because if you take any two elements in G, then their sum is not in G. It is very clear, right? If you can take if M is 1 and N is 2, then it will be 3 by 5. It's not in Z, right? That is very clear. Okay, that should be in G Z. Next is the associative commutative. So is it commutative if you just sum any two elements? Yes? Anyone is asking question? Okay. Is it commutative? Okay, let's try to check. Yeah, it should be commutative because I think so. And associative because all these are real numbers, so they are commutative and associative. So this is always true. And so that's why. Any other questions in that? No. Okay. What is the another question have in mind? Another question is that so if you define a star be an operation from R cross R to R, then again check the same thing for this. A star B is defined as A plus B minus AB. Then you say that so is a star binary, is a star associative, commutative, and is a star group, whatever. So just check these things. So star is associative, star is commutative, star is a binary operation, R star is a group. Star is binary, associative, commutative, group. Just check this these things. Yes, so let's discuss this one. So star is binary operation, that is very clear because A star this thing is in R. So it is a binary operation. Another thing is associativity. How do you check that? It means that A star B star C should be same as A star B star C. Okay. And here A star B is A plus B minus AB star C. So you just check that this is not same as A star B plus C minus BC. And for the commutativity also, you check that it's not commutative, not associative, binary. And for the group, what you need to check for the group, you need to check the associativity, commutativity. Okay, let me see. Is it commutative really? No, no, no. Think I'm misconfusing with this. So it should satisfy this associativity, commutativity, and hence it is a group. So just check these properties. The associativity is this one, another one is commutativity. This is the commutative property and it satisfies this. And then you check what is the identity and inverse. And then you can find out that. Okay, so that's about this. Next thing I want to discuss about the basis and what is a spanning set. Okay, so basis. Okay, so first of all, let's discuss about the spanning set. Let's discuss that. So what is a span? I just denote by a span of a some set S. Then you say that a span of S is elements from vector space V. Um, so S is a subspace of V. I just denote by this notation. So span of S is the linear combination of elements of S. That's it. So it is like alpha i's and SI's where SI is in S. And I by the same index notation I mean summation. So it's like summation alpha I equal 1 to n. So it's just like a linear combination where alpha is enough. Okay. Any alpha is any SI is in S. These are arbitrary numbers from S. So that is span S. And another thing is the basis. Okay. First of all, I tell about the linear independence. So if you have suppose the vectors v1, v2, v3 in a vector space V, then you say that they are linearly independent. v1, v2, v3 are linearly independent. Li, I just say Li. If alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 is 0 implies alpha I is 0. Means if the linear combination, this is the linear combination, this is the span of, this is in the span of this set v1 v2 v3. Yeah, so this is in the set of this one, and you say that if the linear combination exists, then it has to be 0. Sorry, if it is the if the linear combination is 0, then you just say that the coefficients that are contributing to the linear combination are zeros. That is a linear independence. They are not related. They are independent of each other. That is the relation. And when it comes to linear dependency, then you say that alphas are not zero. There exists a relation between these vectors, v1, v2, v3. So that's why they are dependent on each other. That's why there is some relation. That's why they are dependent. But if there is no relation, then they are independent. So that's why alpha is are have to be 0. Okay. And what is basis? of V, vector space V. Whenever I write V, then it is just a vector space. And so basis is just a linearly independent set. So it is a linearly independent subset of that spans. So it is the linearly independent subset of the vector space V that spans V. It means that if you are taking these V1, V2, Vn, then first of all is a basis if of V if the set S is linearly independent, that I have discussed how. And second thing is that V is span S. It means that you can write, suppose V is in V, then you can write it as a linear combination of alpha i's and Vi. I equal 1 to n. Means you can express any member of the vector space as a linear combination of the elements of S. And that is unique way. So this is a unique way expressing. You have unique coefficients which comes under that, right? So that's the definition of a basis of vector space. And now you can show, okay, so I just go to the previous question that I've discussed with you that, okay, so number of elements in the basis. So suppose there are n elements, then this is the dimension. So dimension of a vector space is number of elements in the basis. Basis is unique. Okay, what I would say basis, yeah, basis is number of bases is only what I would say. The basis is unique. No, basis can be many. The set of vectors which are linearly independent and spans a particular vector space can be, that set can be different, but number of elements in a basis are always unique. That is, you always need clear in mind that you take any basis, then the number of elements in every basis are the same. That's very good. That's very true. So number of elements in the basis is dimension. So dimension is unique. Okay, just write then. So this is denoted as dim V. This is the symbol that you use. So there is a question that, so what is the dimension of this subspace W1 intersection W2? Then you can check that what is the W1? What is the basis of W1? Anyone? I just take a hint. How do you write W1? As a span of this vector, right? 0, 1, 0, 0, 0. Similarly, you just replace here 1, here 1, here 1. So you have 1, 2, 3. You have 3 vectors again. So it is a it is a spanning set consisting of 4 vectors, right? Um, yeah, it is a spanning set consisting of 4 vectors. So dimension of W1 will be 4. And hence dimension of W2 is also 4. So dimension of W1 intersection W2 is always less than dimension of W1 and W2. So it should be always less than 4, right? It can be 2, 3. You need to check whatever in the intersection they lie. Okay. So that is the thing. That is all about bases, vector space, subspaces, groups. Yes. So anyone has any questions till now? Let me know. Otherwise, I've stopped here and I just give examples of the basis. So example of, suppose you have a vector space R. So what is the basis of R? Anyone? Basis of R. Let me know. How many elements are in the basis of R? What? There should be only one element, right? Number of elements. And one is the basis. Set one is the basis. And number of element is one. Number of element in R, number of element in basis of R is one. So dimension is one. Is it clear? Okay. And what about the basis of Z? Z is a vector space, right? Or Z is a vector space over which number? Z is not a vector space. R3 is a vector space, and you can show that the number of elements is 3 in the basis. So what is the basis of R3 over R? Basis is just this 100 010, but basis is not unique. You can change your basis, right? Make up thing basis. That is the. So that's all, and um I just discussed the examples of a basis. You try the questions in your assignments related to that, and you will see that how it works. But we will discuss more of this maybe soon, maybe later, I think, or maybe the topic has changed. I don't know. I have to see. But this is all stuff that I've discussed. I will share this PDF, whatever we have discussed today. And if you have any queries, just let me know. This is your first tutorial, so I am doing these things only in this. These are all basics, so you are understanding all these in your classes. Any questions? I'm waiting for questions now. If you have any questions, just let me know. If you don't have any questions, you can leave.
Excuse me, sir.
Yes.
Sir, any
What's your
difference between
name?
subspace?
What's your
Nagaraj P,
name?
sir.
Okay.
Nagaraj, sir.
Yeah.
Subspace and spans are similar, like not
What are you saying? I'm not understanding.
subspace
Okay, subspace.
and
Subspace and
spans.
yeah, spanning set is always a subspace.
They are both are similar. Or
Mm, both are similar. How can you say
trivial
that?
trivial subspace
Means
is
you can write,
subspace.
yeah. You can write every subspace as a spanning set. Yeah.
Just play one example give and explain about
Okay.
that.
Yeah. So I just explain it. So whatever is that? Wait a second. So W1 here, if you see this example, have you understood this example? So
Yes, sir.
W1
Yes, sir.
intersection, yeah. Are you saying something? Okay. So W1 intersection W2 has elements like this. I just explain you. So W1 intersection W2, if you take, then it has elements like this: 0, 0, x3, x4, x5. And these xi's are equal 3 to 5, they lie in R. Then you can write this element as, we can write this element as 0, 0, 1, 0, 0, span of 0, 0, 0, 1, 0, and 0, 0, 0, 0, 1. Okay, is it clear?
Okay, sir.
Yeah.
Yes, sir.
So that is the so how many elements are there? That will be your dimension. Yes.
Thank you.
Yeah. Anyone has any queries? What has been covered in your lectures? I don't know. Has these things been discussed already, or I have to see that?
Sir, discussed. Basis is not discussed.
The basis, okay.
All are discussed in week one.
Okay. I just stop the camera and just come on the camera now. This is my first time taking the tutorial of this course.
Sir, I have a question.
Yes,
Sir, if
which
two subspaces are given, then how to find the dimension of intersection of them?
there is a theorem which comments about the dimension of these subspaces. I think it has been discussed in your lectures, or like there is a theorem which says that dimension of union of two subspaces is can be written as the dimension sum of the dimension of two subspaces and then the intersection subtraction, like that. So I can write, I think, that one if you want me to. Wait. So there is a theorem which says this thing, dimension of W1 union W2 is. Have you seen this theorem before? Okay. I haven't shared the screen. See, wait. Yes, this is the theorem that you can use it.
Okay, sir, thank you.
Yes, welcome. Are you all beginners in this course, or you know this course before? I'm here for 10 more minutes.